So this is the overview of our system. We have divided it into 4 phases: neighbor discovery, parameters exchange, local aggregation, and local training. In phase 1, we introduced the K-regular graph for neighbor discovery, which is used for when we want to find the active and healthy nodes in the network for the formation of ring topology in the parameter exchange phase. I have also explained on how the message flows in the network. So the node wants to send a message, just forward the message to its direct neighbors. Its neighbor also do the same thing. They forward the message to their next neighbors, except the node that it received the message from. And how can the topology be repaired when there are new node or dead node detection? For the first case, which is the new node case, the new node just send a join request to the bootstrap, and the bootstrap randomly choose the edges to break. I mean the K divided by 2 edges to break. And there are 4 affected nodes here, because K is equal to 4 as a design of our system. And the bootstrap also instruct these affected nodes to form the new connection with the new node so that the network now can remain K-regular. For the second case, which is the node failure case, the red node here is the node that should be removed from the system, and there are 4 affected nodes. So the bootstrap will find it out and instruct these 4 nodes to reconnect to each other so that each of them will have exactly 4, I mean K in general, neighbors. And that's all for the slides. Let's talk about the implementation. So in phase 1, the heartbeat loop is very important. For a predefined interval here, the bootstrap and the regular node will originate a heartbeat rumor saying that, okay, I'm alive, I'm healthy, please add me to the global stable for forming the ring topology. And at the end of phase 1, dead nodes, those who did not send the heartbeat rumors, will be indicated as dead and should be removed from the global table. And of course, when we remove the node, there are affected nodes, and we find out them using evict function. So evict function is not that very hard. It just find those nodes which have the degrees that less than k, the number of neighbors that's less than k, and then reconnect each other, avoiding those who are previously connected. And after that, it returns the dictionary of the affected nodes and the new neighbors so that we can send a rewire instruction to the rewire endpoint of the regular node, telling them, now, please adjust your new neighbors lists. And for joining requests, we also have an entry for that, so it's here. So the bootstrap will register the new node with the network using the register function, which is here. It find out, randomly choose the edges to break, and find out which are the nodes in those broken edges, tell them, now remove the old neighbors and connect to the new nodes. It also returns an affected dictionary containing affected nodes and their new neighbors, so that at the end we can also send a rewire instruction for the regular node to update their neighbors. And that's all for phase 1.
Hello, so my name is Wayne. Let's just go for preparations for phase 2. So this right side will be the one for the code of this preparation steps, and this will be the slide that I will go show alongside with the code. So let's just go with the first step. So as you know, Bootstrap will be the one that accepting new node to join the current network. However, we have to have an interval time so that to limit and to restrict new node to join to allow the connected nodes to move to phase 2. So what if the 10-second expired? The current global table will be locked like this. And what is the consequences? The consequences is that new node cannot join, and you have to wait for the next round. And these nodes in the network can move to phase 2. And look at these codes that I have just mentioned. The table is locked. When the floor and the table is stable, that means it is stable for 10 seconds. So it will be locked. Their node will be cleaned up. That is the step that I'm going to mention next. This is the I'm alive status. So no new Bootstrap node will have to track and we have to ensure that all of the nodes inside the phase preparation step have to be active so that it can transfer parameters. So as you can see, nodes that are died during this time will be stored in the dead node table, and the jobs of the bootstrap node is to rewire the network. And these are the rewiring steps. The bootstrap node will have to clean up those nodes that's not showing the heartbeat, and that have to be removed from the table. These are the rewiring steps. Next is the form rings. So we're forming rings by taking a global table like this. However, we have to have a shared thing so that every single node has something that it can be based on. So by sorting the table like this, a node can basically look at its left neighbor and right neighbor to form the rings by just taking its index. Minus by 1 modulo by n can be calculated for the left neighbors, and for right neighbors doing the same thing but plus 1 in modulo by n. And at the end of the day, we will have the rings formations based on these algorithms. However, before moving to phase 2, we still have an originate readies. These steps are a final barrier to ensure that all of the nodes within the network will be ready for the next phase. If some of them is not ready, we have to return, and the guardship step have to be done. That means it cannot process to phase 2, and rewiring thing networks must be happening. That's the step for wait 5. Wait for the barriers. Next is the phase 2. We base the phase 2 on the RPC mechanisms. So that being said, all of the nodes have to start it on gRPC server, like this one. We have the run methods. Here's a ring phase. So run method started on gRPC server. It then forward parameters across the network like this, and eventually the message will travel from nodes to all the nodes, and it cycle back to the original one. So there's the message, there's the payload of it. Especially we have to pay attention to the dead nodes, because dead node is the thing we need so that someone node died during this state, it can automatically redirect and reroute the directions and transfer the parameters to the next one. So these are the functions such as send local model, which is sending the message to the right neighbors, and wait all models, meaning that the nodes have to wait until all of the parameters of all the nodes have arrived. So next step is the stop gRPC server and ready for barriers, the same that I did in phase 1. And that's it for phase 2.
My name is Hoàng Đức Tài, and I will be talking to you about our aggregations in the decentralized federated learning system. I will first show you the idea of our approach. Each node I has a LoRa adapter with matrices BI and AI, representing its local updates. Delta weight I equal to the pair matrices of BI and AI. We also know its dataset size DI, and from that we can get the relative weight alpha I for each participating node I. And with that information, we can then perform the dataset size weighted average in full weight space with delta weight average equal to the sum of I from 1 to n with alpha I and data weight I. Since BI and AI is a pair matrix, matrix multiplication will causing it to be non-linear, so therefore the product of averages is not equal to the average of products and will destroy the low rank structures. And therefore we average in full space, then compress it with singular value decompositions. Basically, we are trying to decompose the complex matrix data weight average into much simpler matrices. And afterward, we will keep the top rank R singular values and rebuild the new matrix B and the new matrix A. And now let's see how this map implemented in code. And now we will continue with our code implementations of the aggregate function. It was first starting with loading its own local adapters. And then it will load the adapters from the peers, which is delivered by the phase 2. And after that, we will basically calling our merge functions with the target rank of 16 after we have knowing the statics and the dataset size. So in our merge functions, we will be starting first with trying to get the total numbers of samples in all the nodes in the systems, and then we will have the weight for each corresponding node, and afterwards we will trying to load the LoRa prefixes constructions and running the LoRa weight keys, and moving on we will have this section of code here, which is basically the reconstructions and the SVD. Starting first with, we are trying to update the low rank update of matrix BI and the matrix AI, and multiple it by the corresponding weights, which is will then be adding to a total sums called delta sum, which is exactly the delta weight averaged for that layer. And then we will calling torch linear algorithms single value decompositions to decompose the matrices into simpler matrices before we recompose it into new matrices BI and new matrices A. And for the non-LoRa keys, it will be handled simply by just applying normal weight average from the weights we calculated before.
So this is the last part of our project, which is the phase 4 local chaining. We use the base model as hacking phase, causal LM, which is fine-tuned using LoRa and LoRa adapters to make it more parameter efficient. The set is split into chain validation and test with just style, message mapping, and tokenization. Also, we use strategies such as early stopping and evaluation checkpointing. Here are the diagram of the structure and architecture of LoRa and LoRa. When we implement DFL in real-world scenarios, we encounter and brings to light significant challenges across both AI and system-specific aspects. First one is between the communication and the quality trade-offs. The second is the partial participation and robustness. Third one is heterogeneous data stability. And the final one is hardware constraints and precision. Also, there are some trade-offs in our architectural design. First, between LoRa and LoRa and the full fine-tuning, we use LoRa and LoRa. Although the full fine-tuning is simpler, but they ignore data imbalance, potentially biasing the aggregated model. Also, we would like to use the weighted instead of the default averaging, although it is simpler, but it's not as effective, as efficient as the weighted. Also, by reserve low rank structure and keep the adapter size compact, we use the SVD refactorization after aggregation. And finally, as the nodes vary in hardware, CPU and CPU capability and memory, it ensures the pipeline runs reliably across various hardware without sacrificing the model integrity. Now let's take a look at our result after training. To measure the model quality, we use the cross-entropy loss and test perplexity. As you can see, the gap between the weighted DFL is much more smaller than the gap between the result of the local-only benchmark. Also, hospital A have to suffer from a trade-off as its test perplexity increased from 7.26 to 7.69. However, by using Fed IC approach, it will improve the stability for the system. This diagram shows the simulated evaluation loss curve. As you can see, the weighted DFL model converges smoothly and is just a little higher than the centralized by 0.03 and in evaluation loss at the last training ground. Now let's move on to the code part. First of all, we will get the data size for the weighted calculated aggregator. Then we'll enable the LoRa gradient, but loading the dataset into Hugging Face dataset format so that it can process easier. Next, we will load model and tokenizer of the model from Hugging Face. And here we will set up the LoRa to use the weight decompose and make the stability improve. Here is the methods that will process the data and also save and keep the checkpoint. at every 10 epochs by using evaluation loss. This is the chaining arguments. As you can see, we will use the per divide chain path size as 4. Current accumulation steps is 4, so the total path size is 16. Then with the linearity is 10 power of minus 4. This step is 10. Num chain inbox is 30. And we use a data loader to load the dataset into the model more faster. And then we will initialize the chainer by using the chain dataset, evaluate dataset, the model, the arguments, and the data collector, as well as the full methods. Finally, we will start the training and save the final model after it completes the training process.
Okay, now we are going to do the demonstration part. So we have 3 demonstrations. First is a spin up where we're going to launch n nodes and watch the round. Second one is to see the fault tolerance, and the third one is to see the scalability. Okay, so I would choose to open 5 nodes and we shall watch. This is the bootstrap, and the other will get populated gradually. As you can see, 5 nodes has been launched, and they are connected with k neighbors. We set k equals to 4. Now it is going through the phases. It's currently at the phase 2, and you can see the rumors are being sent, and the addition and the informations are getting transferred. You see the neighbors. Okay, and now we can test the chatbot. I have a fever, headache, and nauseous. What do I do? And this could take a while. Okay, so we got response from the LLM GPT-2. Okay, so now we're going to test the fault tolerance. It will spin up 5 nodes, and then we can choose a node to kill. Okay, so I will kill the second node, the third node, and it's being killed. Now it's gone, and you can see it is working just fine. Now we're going to test the scalability of the system. So it's going to spin up 3 nodes, and then we're going to type add, and it will add in the new node. So 4, 5, 6, 7, 8, 9, 10. So it's going to spin up 10 nodes. Yep, and it's working just fine. And that's it for this demonstration part. Thank you for listening.